Welcome to Extra Credit. In the last episode, we learned a lot about waves. Now let's learn a little bit more with a little bit of math. We're going to talk about a principle called diffraction, and we're going to talk about one of the experiments which was the major argument in the turn of the century for why light behaves like a wave. Let's picture that we have a material with two holes in it. Here's hole number 1 and hole number 2. Now let's picture wave fronts, and let's say that we're using red light. And so these are fronts of the light waves coming towards our screen with our two holes in it. Now let's say we have another screen over here. Now what we would think would happen if light was a particle is that we'd probably just see these portions right here, the portions of the light wave front. We'd probably just see these portions make it through the holes, and they'd be projected on the screen right here and right here. Now we don't see that, and we have setups to show us that we don't. Over here, I have what's called a diffraction grating. And this grating has very, very, very tiny little slits in it. And if I take a laser set it up against the board here, and put my diffraction grating in front of it, I end up seeing 1, 2, 3 lasers. 1, 2, and 3. Whereas if my laser were cleanly passing through just 2 slits, we would probably only see 2 dots, and those 2 dots would be equally spaced. Well, what's really happening here? Let's take a closer look. Let's say I replace my screen, and I continue taking these wave fronts, these portions of light, lots of light waves, all stacked up in one front together, moving towards this boundary with the 2 holes in it. Well, if you were to be in a pool, and you were to have very, very, very steady water, and you were to have a hole between one set of water waves and another set of water, you would actually see the waves do something like this. They would bend out from both of these. This is called diffraction. And what happens is when waves pass through from one boundary through a slit to another, we end up having this bending effect, where the wave that actually makes it, or the portion of the wave that actually makes it through this slit, will actually bend out and spread out as if it was a circle. Now you'll notice that we have some specific spots here. Here, 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 where the waves actually overlap. What we're going to see at those spots are some constructive and destructive interference. Since this is all the same light, we know that depending upon how the wavelengths stack up on each other, they're either going to positively interfere with each other, create a nice peak like we saw in the Rubens tube, or negatively interfere and actually deconstructively impact one another. Therefore, we don't see any light, just like we saw on the valleys of the Rubens tube. So we just talked about diffraction. Now let's see a real-life example of it. You'll notice that I'm shining a laser onto the board. But I'm not getting just one spot, I'm getting 3. And actually, if we go a lot wider, you'd see a couple more. Well, this is the point where the laser is actually being pointed, right here. Yet I've got a point that's almost as bright right here, and then another one that's almost equally as bright as this one on the other side. And if you were to go out even further, you would actually see points that are not nearly as bright. So if we were to compare this one to this one, to this one, you would see that the closer we get to the center, right where the laser is pointing, that we get a very, very bright spot there. This is called diffraction. We're witnessing the phenomena right now. But this all went back to one of the very, very first arguments for the wave nature of light. Now you would think that if this were a particle, it would have just hit the wall. If I was putting it through slits, it would just hit the wall and pool in 2 places or 3 places. In this case, we're getting 5 places that we know of. 2 on that side, 2 on this side, and 1 in the middle. Well, let's think about what's really going on. Let's say we draw our diffraction grating. And recognize that the slits in the grating are very, very, very small, and I am enlarging this quite a bit. So make sure you understand that this whole portion of what I draw on the board is massively enlarged. Let's say I'm shining a laser, some red light at it. And let's say this is the laser wavefront. And let's say the wavefronts are evenly striking this slit and this slit. And let's say we could actually measure the distance between the two. Well, we've got this center dot, and that's appearing on our whiteboard. So let's go ahead and make that the center of our screen. So we're taking a look at this experiment in 2 ways. 1, we're seeing it as it is on the board, and 2, we're taking a bird's eye view with an enlarged look at the screen, and we're going to see what happens as if we were looking from above. So what we're going to do is we're going to compare rays. Now a ray is just one wave of light, and seeing what happens when it moves across this distance and then hits the screen. So let's take our first set of rays. We'll call them ray 1 and ray 2. And we know that they're going to meet up, because we're looking at it right now, that they're going to meet up right here in the middle. So let's draw a line for one ray at one slit, and then another ray from the exact same position. So we get one spot, we'll call this the brightest spot. And then, since we're drawing from this spot on this slit, we have to draw from the other spot. It is the exact same, symmetrical on the other slit. So what do we have going on here? This is one ray that's diffracting out and then interfering with the other ray. So there are our rays. Finish it off. So we get these two rays meeting up. Well, here's what we should notice, and here's what I want you to notice, is that if I were to measure the distance from the very, very center of the slit, all the way to where our positive interference occurs, you would hopefully recognize that if I titled this ray number 1 and this ray number 2, that they would both be traveling the same distance. And therefore they should be adding up. And if we were to draw transverse waves on the board, we would have a peak and a valley and then back up to a peak. But at this point, the brightest point, right here on our screen, we should have two waves adding together, meaning constructively interfering to make a bright spot. So I should have two waves, peak to peak and valley to valley, and that means we're getting constructive interference. So that's our brightest spot. Well, let's take a look at what these rays may do if they change positions. Since these rays are traveling the same distance, I know their wavelengths are going to meet up. So I'm going to call this m equals 0. I'm going to call that the 0th maximum because that's the most positive interference that is going to occur. Well, what about this spot? Or this spot on the other side of the brightest? I see that yet another spot and another spot, equidistant from the center, also occur. There's nothing in between, nothing here, nothing here. Well, let's take a look at what our rays do when we refocus them on either of these pieces of constructive interference. So check out ray number 1. Ray number 1 travels just like this. And here's ray 2. Oops. So here's our new ray number 1. And here's our new ray number 2. I think I'll just erase these beginning guys so you don't get confused. So if we were to take a look at the difference between the two, we were talking about the distance moved by a wave. Well, if you look, and if we were to actually physically measure with our ruler, even our lines on the board, we would find out that ray 1 traveled a longer distance than ray 2. And that we can actually figure out what that distance is based on similar triangles. If I were to measure this distance, I'll call that distance x. If I were to measure that distance from this first bright spot right here to our brightest spot right here, so from our bird's eye, that's here to here, if I were to measure that distance and perhaps measure the distance to the grating, which I'll call a distance L, I could probably find an angle here that I'll label theta. Now, here's how this works with our rays. I want to know how much longer of a distance ray 1 traveled from ray 2. So what I'm going to do is I'm going to pick this spot where our ray originated from, and I'm going to drop down a perfectly vertical line, or as vertical as I can make it, so that it makes a 90-degree angle with ray number 1. If I drop down a perfectly 90-degree angle line from this point to this point, that means this point and this point are equidistant from where our maximum is occurring. And that means that this distance right here is the extra distance traveled by ray number 1. Now you say, okay, that's great. What does that mean? Well, if I see a bright spot, and we'll notice that it's not as bright as our brightest spot, that means we're getting another constructive interference. Now it's not as bright. You may say, why is that? Well, these waves aren't they're meeting up really, really close, but they're not meeting up exactly. Not nearly as concisely as these two are. So it's still constructive interference, but it's just not as strong of a constructive interference. So it's all about knowing exactly how many extra wavelengths we need to get constructive interference. Well, in this case, I know I need a peak and a valley to meet up with a peak and a valley to get constructive interference. Well, if I were to say, bump this wave over by a half wavelength, remember a wavelength is a whole peak to a whole valley. If I were to say bump it over by half, I would end up with a valley and then a peak. And that wouldn't create positive interference. This would in fact create negative interference or destructive interference. That's what's happening between this bright spot and this bright spot. There's no light here. because all the light waves that interact between this spot and this spot actually cancel each other out. So what would I have to do to get another constructive interference? Consistent with how many extra wavelengths in this extra distance ray 1 actually travels. Well, what if I bumped it off? Let me define this, a bump of 1/2 of a wavelength. Remember, wavelength is lambda. What if I bumped it over again by another 1/2 wavelength? Well, then you see we get back to peak and valley. So I moved this over. That means I'm back to constructive interference instead of destructive interference. So we know that if I were to say call this m equals 1, I would know that at this point I would be getting 1 extra wavelength of distance here moved by ray number 1. And that's why I get positive interference. Now we can measure lambda. We can figure out how many wavelengths actually exist by making a couple of measurements. So first I get L and X and theta. Well, if I wanted to know the relationship there, notice that from this bright spot to this bright spot, I could measure that. And I could also measure the length from my whiteboard to my laser. Well, I know that the relationship here between this angle and this angle is that they should be similar triangles. So that should also be theta. And if I could measure this distance, I'll call this d, between the slits, even though they're very, very small, I would know that this extra distance covered by ray number 1 would be the opposite side of our triangle. Here's our angle. This is the opposite side. This is opposite the 90-degree angle, so I know d would be the hypotenuse. I know the extra distance traveled by ray number 1 would actually equal d times the sine of theta. And if I wanted to know how many wavelengths could actually fit in here, I'm going to say, hey, I know d sine theta is the extra distance traveled by ray number 1, and I know in that distance I'm going to get a certain number of wavelengths. Well, I know that's going to equal some number of wavelengths m times the actual wavelength of the light. So m equals the number of extra wavelengths traveled by ray 1. So that tells me, this formula can tell me whether I'm going to actually have an appropriate number of wavelengths. If I have m equaling 1, guess what? I'm talking about the first maxima. If I have m equaling 0, guess what? They're traveling the same distance and there is no extra distance. So this whole equation would equal 0. Recognize that that would also happen for this one. This one would be also m equals 1. So the relationship here is described by this triangle versus this triangle. And recognize that this is way enlarged. This point would actually be very, 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 very close over here to where our two slits. Our two slits are so close together that this triangle and this triangle are very, very, very similar. So the relationship here is if I have the length from the laser to the screen and the distance between my maximums, which would be this distance right here, this bright spot to its first not as bright spot, is going to be that the tangent of theta is going to equal my opposite side of my triangle x over L. Now, here's the deal. We are talking about such small angles when we talk about the double slit experiment that we can simplify our formulas. That the sine of theta, since theta is so small, is really going to be theta. It's not that much different. And we're talking about decimal places of into the thousandths, which are very, very small and very, very hard to measure. So I'm going to simplify both my formulas, and I'm going to say that x divided by L is actually going to equal theta. And I'm going to say that d times theta is actually m over lambda. Now, if I wanted to measure any of these things, let's look at my measurable values. I can measure x, I can measure L. Usually lambda is a known depending upon your light source. Therefore, I could actually measure the distance between the slits and see how close they are. So in this case, I see that I've got a lambda here and a lambda there. Well, if I want to combine these formulas, I can solve each for lambda and then set them equal to one another. So in one case, I have d times theta equals the number of extra wavelengths times the actual wavelength of my light. And my second formula is theta equals x, which is the distance from bright spot to bright spot, our brightest spot in the middle to another bright spot, over the length or the distance between the actual light source and the screen itself. If I set this equal to this, I know I'm going to have m over m times lambda divided by d. So I'm going to have m times lambda divided by d equals x over L. And if I wanted to solve for d, which is the distance between the slits, or if I wanted to solve for any one of these variables, you would have to take the specific measurements that apply themselves in our formula. We have to know which maxima we're talking about. If we wanted to know our wavelength, we'd have to measure the distance between the slits, the distance between the maximums, and the length to the screen. So let's solve for the distance between the slits. I'm going to multiply by L. I get L times m times lambda over d equals x. If I'm going to solve for the distance between the slits, I'm going to multiply by d on both sides, and then I'm going to divide by x. And I end up with L times the number of extra wavelengths times the actual wavelength of the light divided by x equals the distance between the slits. And that's how we know the distance between our diffraction grating, or how we could determine the distance between maximas. Now, I might have mentioned the point. This experiment paved the way for modern optics. It paved the way for us to understand how contact lenses work, bifocals, hearing aids. Our understanding of how we can cancel light waves and even sound waves has been monumental to our development as a culture. I hope you enjoyed it. Join us next time on Science.